So trying to keep with this program or tendency of like recording myself like working on stuff just to try to stay focused and motivated, and then over time for these to become like more like they can become edited into like tutorial videos and stuff once I myself understand the stuff better. So like usually I was not doing that for computer stuff, but I'm actually doing this for this math paper, which, for me studying math is like very hard. It's like you're just trying to break apart these definitions and actually understand them. And then when you actually understand a new concept, for me it can take like easily like a week at minimum, but it can take much longer to actually like keep mulling something over from different angles. But anyway, I'm just gonna try to. One reason that I want to do this is because I want to try like seeing if I can move through a mathematical paper a little bit faster than I normally do. Um, because I just tend to get so caught up in just like one definition, and I think it's a good thing, but it to like just analyze something, but it's just also useful to be able to kind of move ahead and yeah, I don't know how to say this. Like sometimes if you move ahead, you actually get some answers to your questions, and it's like it's good to take in like a nice chunk of information at once. Kind of, in some ways, it might be more effective or efficient than one might realize. I don't know. So anyway, where's that paper? Oh nope. Oh. Okay, so I'm gonna skip the introduction and I'm gonna go to where they start talking about, like they actually start defining stuff mathematically. And I'm just gonna be like really open here that I'm probably like out of my depth, but it's, as I said, it's like just trying to show my own process of studying mathematics. Okay, so chapter 1 is like introduction, or section 1. Section 2 is like it just looks like mainly terminology, I think. And then here, section 3, they start like giving you definitions to work with. So I've heard this term vibration a lot, and I know that eventually I will be studying it. As of right now, I don't fully understand it. Here, the author is saying something like, 1 second. So apparently there's some kind of like comparability between presheaves and discrete vibrations, because it appears that the author is like saying, oh yeah, you could describe models of a theory with presheaves, like this guy Owodi does, but I prefer to use discrete vibrations. So obviously that implies like there's some kind of loose like substitutability as a format. Um, Discrete vibrations are convenient for the study of the two category of models of a type theory. A model of a type theory will be a cat valued 2 functor. And yeah, like I have a lot to learn here. So I know that like my 1 second. Let me think about this. Okay. So in general, I think of a category as objects and morphisms. And I think that a 2 category has like morphisms between morphisms. And that you can actually think of objects as you could call them like 0 morphisms. And if we did that, it would appear that whenever we call something like an n morphism, like a 0 or a 1 morphism or a 2 morphism, it's just because morphisms, like formally, they're just, I believe they're basically just a relation, like a binary relation. So actually, let me open up some like drawing software 1 second. Okay. So like, if we have these objects, and then we have morphisms or arrows between them, then from the perspective of formal logic or set theory, you have a set of elements, and those are the objects, and and these arrows or morphisms are, I guess you could say, like informationally encoded as like, 1 second. If I just, like, let's say I call this F. Well, in order to sort of state that F exists, to define its existence, all I really need to say, 1 second, A, B, is that I'll take A, and I'll take B, and let's see, let's put it like this, and I'll put them together in a little ordered pair, and I'll just say this little ordered pair is is in this set I have things I have, and I'll be calling that like the set called arrows. I think this like way of presenting it is valid. Yeah, but I might need to think more about that. But what that means is, okay, so now I'm thinking about like, what if everything is considered a morphism, like a 0 morphism, 1 morphism, 2 morphism, well, then what if everything could be considered like an ordered pair? Okay, so like for the 2 morphisms, presumably, well, now let's just call this like, I don't know, for now we'll just call it 1 more. So presumably for the 2 morphisms, we'll just take like 1 of the 1 morphisms and 1 of another of the 1 morphism, and I'm not thinking right now about if this is like a valid morphism, like if these are actually if this is even possible. Doesn't matter, let's just make up some other morphism that exists, D and G, and as long as we have an ordered pair, hypothetically, we have a 2 morphism. And that just means that this number is just referring to the number of the set of elements that you're taking pairs from, the way I see it. Which opens the question, are these so-called zeromorphisms, can they be seen as ordered pairs of something? I'm not really sure, but maybe you could say that like they're taking ordered pairs from the empty set or something. Or actually, we could do this. Whoopsie. Yeah, I don't know if that's valid, but I'm not gonna get too hung up in the details right now. So I probably need to learn a lot more about how to define a 2 category. But then, I hope we can say like a functor, like it's just like a mapping, but it's on an object it's on a thing which often has like multiple subcomponents, like a category. I've seen it sometimes defined as like I think I've seen it as defined as I'm not sure if I've seen it defined as like a tuple or a pair or something, but the point is like it's a thing which is actually 2 things. It's a collection of objects and it's a collection of arrows. So if you're going to have some kind of mapping on like between such things, it kind of I don't know if this is like a valid mathematical term, but I think of it as like it almost like decomposes into multiple mappings. So it's actually a mapping on the objects to the objects, and it's a mapping on the arrows to the arrows. So like I'm gonna just think that, okay, so for a 2 category, a 2 functor is a mapping on the objects to the objects, the arrows to the arrows, and then the arrows between arrows to the arrows between arrows. Or in other words, like each of these sets is just getting mapped. So the 0-morphisms, the 1-morphisms, and the 2-morphisms. And I should probably look at like some diagrams that express the conditions of this mapping. I think they're often called coherence conditions. Yeah. See if that's enough to like move ahead a little bit. This section is mostly devoted to rephrasing the theory of natural models, blah, blah, blah. It might be new to the reader. The push forward along a representable map of discrete vibrations is given by the pullback along the right adjoint. Okay, so I am still working on understanding like functors, and I know that I'm not going to really understand adjoints for a little while, but I want to. So I might like pretty soon get stuck, unfortunately, but we'll see. Okay. So I do think I know a tiny bit about push forwards and pullbacks. One second. Okay, so the push forward along a representable map, discrete vibrations. Actually, maybe they'll just define it for us, so I can move ahead. But I understand push forwards and pullbacks to be something like this. So I believe it's called a span. And I guess if we want to think like set theoretically, you know, that's just two functions, and yeah, let's just say we have a set of like 3 elements or something. Set of like 1 element. Whoopsie. Set of like 4 elements. So, okay, that's like the singleton set, so there's only one possible function. This set is larger, so we already know it can't be surjective. This is injective. This is not really important. I'm just practicing like thinking about diagrams like concretely when I can. Okay, so this is a span, and I'm pretty sure, but I need to think about this, that for a span, yeah, I think for a cospan, we can have a pullback, but I'm going to just check this with some reference material. So again. Actually, I'm not sure if there's a difference between a push forward and a push out. But I think, because I remember seeing diagrams that kind of look like squares, and I think that the pullback is like this, and we have to say that this diagram commutes, unless we can just understand that such diagrams are always understood to commute. I mean, when we draw diagrams, that we just assume that that's a commutative diagram. So basically, what this is saying is there is some object where when you compose the morphism, this morphism with a morphism from that object, and this morphism with a morphism from that object, then all of a sudden those composed arrows are the same. I might be mixing this up with the equalizer. I'm going to have to look up the definition 1 second. And again, just to make this concrete, let's make that little equal sign. Let's just try some random sets and see what happens. Let's say that A is a singleton set. Earlier I said the singleton set, and I realize now there's not just one singleton set. And let's say, just to be weird, I'm just being like spontaneous. I don't know what's going to happen. I'm also going to make C a singleton set. And then I'm going to make B have 2 elements. And it's a cospan, so the arrows are actually going in. And now, let's see what happens when we make D have 3 elements. Well, singleton set, all go to the same thing. Here we have some options. But I think there's only 2 options up to isomorphism, because you can either have all of them to 1 element, or you can have 2 to 1 element, 1 to 1 element, and there's no other possibility, which is kind of interesting. Okay, now let's follow these arrows and see what happens. This goes here, this goes here, this goes here. I'm composing on the left. This, okay. Now it's obvious, because the sort of like final destination is the singleton set. Obviously, like you could have any set here, you could have any set here, and you could have any set here, and they would all just end up in the same place. So that's probably some fact that I hadn't thought about. The singleton set is, I believe, a singleton set, any singleton set is, I believe, the terminal object in the category of sets. And the terminal object, the definition is, I think, or believe, that it's an object for which there is only one morphism. There's one and only one morphism. From every other object in the category. And yeah, that might be wrong, but now I'm just realizing that usually when we have things that are dual, we use the word co. So like we have a span or a co-span, and I'm believing now that the initial and the terminal object are dual, but for whatever reason people don't use the terminology like co, like, which maybe that could be interesting. If we did that, we would like see it differently. Like what if we just called it like the unary object or something to express how, there's just one morphism, and then like we just use the word co to, express the direction of the morphism. I don't know. That's a question for another time. I like this example because it taught me something, but it doesn't really teach me that much about this, and I am going to go to the reference materials now. Okay. In situations like this, sometimes it's a hard choice. The NLab is like more obviously like inherently categorical and interesting, but sometimes it's actually harder because they define like simple ideas in category theory through like even more complex ideas in category theory. Wikipedia, it's like more conventional, but sometimes it's almost like, I almost find it like distracting, like there's almost too much information. So we'll see what happens. Pullback. Category theory. The pullback is the limit of a diagram consisting of two morphisms with a common codomain, which I believe is called a cospan, unless I'm wrong about that. The pullback is written P equals X times with subscript FZG, which are these are the arrows coming from these objects into Z, Y. I want to think more about that. Usually the morphisms F and G are omitted from the notation, and then the pullback is written X times subscript Z, Y. The pullback comes equipped with two natural morphisms. This is this thing like natural transformations, natural isomorphisms that I still haven't really understood at all, but I know that I'm going to eventually and that I need to. P to X, P to Y. Like one question I want to ask about this is, since they're using the symbol that is also associated with the product, but then they subscript it with this object, it obviously, to me, it implies like there's some kind of analogy here with products, and that's something that I want to think about more. The pullback of two morphisms need not exist, but if it does, it is essentially uniquely defined by the two morphisms. I'm wondering if this has a specific meaning, or if it's just kind of like a synonym for like basically or something, because in mathematics people tend to become extremely precise. So I'm asking myself, can we get rid of this word here and just say it is uniquely defined by the two morphisms? I don't know. In many situations, X, pullback, Z, Y, I'm not sure if there's a cool way to read this, may intuitively be thought of as consisting of pairs of elements with X and X, Y and Y, and f of X equals G and Y. F of X equals G of Y. Yeah, so push out does not equal push forward, I believe. Yeah. Push forward, category theory. Or maybe they do. I don't know, but this is so much information that I'm just going to get distracted. And I'm not going to worry about that right now. In any category with a terminal object, like the category of sets, I believe, the pullback is just the ordinary product. Well, that's interesting. That's really interesting. Monomorphisms are stable under pullback. This is like some good concrete information that I should study. But as I said at the beginning of this video, like mathematics is like hard mental work, and sometimes you're just like, I could probably spend like a good hour just thinking about that. Maybe I should, but yeah, we'll see what happens. Okay. See if we can get back to this. I still don't know if this is, because yeah, push forward along. I think this, I'm just going to say this is too much for me. 1 second. I'm going to say this is too much for me, and I'm not going to try to understand that yet. And honestly, this is also too much for me. But it's okay. A discrete vibration is a functor such that for any object and arrow, this arrow is from J, which is, I think it's commonly used as just like, oh, actually, I've seen J often used in the definition of diagrams. Diagrams are just functors. And J often represents like the indexing category. But maybe not in this case. P of A. Oh, P is the functor. Okay. So that means that, so we have a functor and it's going into this category S, and that means that, I don't think they say it, but I think we should understand that J is an object in S, because P of A is basically has to be an object in S, and so U has to be an arrow in S as well, I believe. There exists a unique arrow. So wait, so for any object in A and any arrow in S, which is pointing at the functorial like map result or mapping of A. Actually, this sounds like something I can draw. So we have, I don't know, this is kind of how I like to draw categories right now, just conceptually. We have objects, we have arrows, and this is a category A. And then we say this is like object A. And then we have this category S. We've got some objects. Okay. Then we have a functor P. And P is mapping all the objects over to something. Whoops. And it's mapping all the arrows over. I still have not taken the time to really understand functors that well. Like, think about them. They're kind of like logic, you could say, like things you can understand. But I'm pretty sure this necessarily follows. If the functor is going to map this object here and it's going to map this object here, then just immediately by definition, because the arrows are just defined in terms of the objects, this arrow has to be mapped to this arrow. Like, I should take them a moment to like absolutely prove that with certainty, but just off the top of my head, like, if that was not the case, it would just be like a very random scrambling of information that I don't think it would have. Yeah, actually, I guess I shouldn't say that. I shouldn't say that I know until I really examine it, but I'm guessing that it just wouldn't have enough, like, coherence or whatever you want to call it to be like a algebraically studyable matter. So anyway, we got the arrows. The arrows are being mapped over, and yeah, I don't know if this mapping could make sense or not, but I'm just doing it to sketch out some, like, a general idea, let's say. This is A, and now we know that this is P of A. And so basically, one way you can think about this is that if the domain of a functor is just thought of as like an indexing, like an indexing thing, then you can also think of like the objects in the target category. You can also just write them with the I don't know what you would call that, like, well, whatever, the object that's being mapped to it. You could also write it with like a subscript if you wanted to. Oh, whoops, no, wait, that's not correct. Or is it? Yeah, actually, I think so. Anyway, there exists a unique arrow. Okay, so we have the object, we have the arrow, and then now we know that this U, it can be anything in this category. That any map from any morphism from any other object in S. So now change colors quickly. So this can be U, this can be U. Like, if this morphism exists, that's an important point, but it could be U. There exists a unique arrow M from B to A. Now we're back over here. And it's always, I think I've learned that's really important when you read these definitions to clearly like recognize and differentiate between like um you know, for any object in A. So like we know that there's no question of, oh, but does it exist? It's like, well, yeah, it's just if there's an object in A, then you have an object. Well, actually, darn. Yeah, never mind. This is like what I would think of as like a contingent darn. Maybe I take this back, but it's healthy to like think about this stuff. Yeah, actually I know how to say this. Um it's like a contingent condition because if there is an object but for some reason there's no arrows into P of A, then it's like you don't need to worry about what comes next. So it's like you have to check this condition for all examples of uh, for all examples of yeah. This is like one of those things where you think it's really easy, and then when you start to think about it, it's like your brain needs to like go through all these sub kind of considerations before you like solidify your understanding. So I'm just gonna skip ahead because I feel like it's not like mystifying, but there's just weird little angles that I can look at it from. There exists a unique arrow M B to A. So what this is saying is like the arrow is unique, which would mean that it is going to determine some object B that it comes from. But in the home set between B and A, there can be multiple arrows. So it doesn't. So the thing is that like M determines B uniquely, I think, but B does not determine M uniquely. So that's why, yeah, I just think again that's like one of these little things about the definition that you should think about. So anyway, let's assume that we find our B and we find the M such that P of M equals U. So then we map the arrow to the arrow, and that makes this P of M. Sometimes instead of like thinking about it a lot, I just try to commit the words to memory. Like I just try to like at any point in the day just be like just say the words like a script, like just memorize them. Discrete vibration, like I'm gonna try to not even look at the PDF right now and see if I can say what I just read. A discrete vibration is a functor P such that for any object A in the category A and any arrow U from object J in category S, to object P of A in category S, there exists a unique arrow M from object B in category A to object A in category A, such that when functor P maps M, it equals U. And I'm not gonna like spend too much time. There's like an optimal point where you're like, I think I've got it enough in my mind to let my subconscious do the work later in the day. I'll just be turning that, I know now at this point I'll be turning that definition over and like thinking about it, but I'm actually going to get like too stuck if I keep thinking about it too much right now. So I'm actually going to move ahead, even though I don't truly like understand the significance. Okay, such unique arrow is denoted by U with a bar subscript A, which is defined as U star A to A. And I actually don't really know where the star thing is coming from. But I can just think about it with this notation because, yeah. Okay, so the vibration. Oh no, that's not the vibration. Okay, so the unique arrow in S is M, but we can write it as U A superscript. And let us remember that is the kind of original object in A that kind of, I don't know. It's the first part of the definition anyway. And U is the morphism in S. Wait, let me think about this. Okay. Okay. See, this is helping me actually. I'm thinking about this better now. Because these, okay, yeah, I get this better. So P is a functor. So it's going to be mapping every object in A and every morphism in A to something. And so the condition of this functor is that for every object that it's mapping, which is kind of represented by A, it's like a variable object, and it has to map. Once we map it over, then there's like a second round of like variables, like for all the arrows coming into the object after it's mapped over, all of those arrows have to be expressible as a functorial mapping from an arrow in the source category. Whoopsie, 1 second. Undo. So now I see it like this. We have, for any object in this category, we know that the functor is mapping it to something. And once we get over here, there's going to be some set of morphisms into it, even if it's an empty set. And for this to be a discrete vibration, all of these arrows have to be expressible. They correspond to a unique arrow. So, in other words, I think that's a way of saying, wait, let me think about this. Yeah, I think it's almost like injectivity or something. Like, I think it's saying that this arrow cannot be mapped. This arrow cannot be the result of multiple arrows over here. So this, you cannot have, this is a no-no, I think. Because it says, for any arrow u, there exists a unique arrow, such that p of m equals u. In this case, there does not. There exists two. And unique is just a synonym for one. It's kind of a cool way of thinking about it. So now I'm just thinking about this as saying, I'm going to think about this like this. I think there's like these terms like full functor, faithful functor. I think faithful functor is something kind of like that, like injective on home sets or something like that. And so we can kind of compare discrete vibration. Like I'll just write for like maybe like a future question or something. How does a discrete vibration, whoopsie, like I'm not saying that it equals it, I'm saying like how similar are they when I write this? How does it compare to a, let us say, faithful functor? Cool. And again, I am actually not trying to understand everything like perfectly. I'm trying to get it to a point where I feel like something has kind of, my mind has gotten like, it's almost like it's broken apart the pieces enough for there to be going something on, like, how to say this? There's like enough in my mind now that it's going to start working on it autonomously. Like, I don't have to be studying math. Like, I'll just be doing something, but my mind will be like coming back to, reassessing the situation. It's like you have to kind of break through the impenetrable like definitions and diagrams enough to then kind of put them back together. Let's put it that way. So I don't understand this, but it's enough for me to like move on a little bit. When P, which is the discrete vibration, oh shoot, no, sorry, P is a functor. When it is a discrete vibration, we say that A is a discrete vibration over S, okay, and refer to the functor P as PA. Fair enough. I'll just highlight that because it's just a matter of terminology, and I'll probably need to remember that. Whoopsie. Maybe, I'm not sure. Maybe I'll use a different color for like terminology or something. All right. For a discrete vibration A over S, a discrete vibration B over T, and a functor between the target categories. A map of discrete vibrations over F is a functor. Okay, I'm not going to worry too much about this. Like, I feel like so many things in category theory, um, it's like, it's basically just a map and it has to meet some coherence conditions. And you can kind of, you should spend a lot of time thinking about what they are, but you can also just be like, I'll study them later because I understand the idea. Like, it just has to correspond in a certain way. Like, it has to fit in with like the whole categorical structure. So, like, you know, it's not ideal, but I'm gonna say like I'm not gonna get like slowed down by that right now. A map of discrete vibrations over the identity functor. Okay. Oh, 4 discrete vibrations, A and B over S. So right now my mind is honestly like getting like tired. It's like, oh, I should take a break or something. But because I'm like filming myself, I want to challenge myself to like get somewhere. It's gonna be hard, but I think like if I could challenge myself to get to like here or something, that would be pretty cool. Okay. A map of discrete vibrations over the identity functor is called a map of discrete vibrations over S on S. Sorry, the identity functor on S is called a map of discrete vibrations over S. So, okay. Simplifying all this, I think just one simple point I want to take away from this all is that discrete vibrations are certain types of functors, and you can map between them only if you already have a functor between the two target categories. And to me, this kind of reinforces the idea of a functor where the source is like kind of like just an index. It's like there are different ways to think about it, but sometimes it's sort of like all the focus is really on the target, is the way it feels to me. So what we're really saying is if we have two like categories, S and T, and we have a functor between them, something like, oh, we have a discrete vibration from some other category to S, and we have a discrete vibration from some other category, B to T, then we can map between the discrete vibrations, basically. Let's just say that. And I'm also asking myself, so what? Like, so if we have a discrete vibration into some category, obviously, like, the question is, what does that tell us? Like, is it the case that only some categories can have discrete vibrations into them, or is it more the case that, or is it more a matter of the source category, or what I'm calling the indexing category? Is that what is going to determine if a discrete vibration is possible, or is it both? And yeah, we'll see. But right now I'm just thinking about discrete vibrations as functors, which are like, they have a very kind of particular kind of precision. Like, it's just a certain like way for the morphisms that are being mapped to correspond like very kind of tightly and precisely, or something like that. So for discrete vibrations, A and B over S, and let me remind myself what that means. Okay, over S, wait. Over S. 1 second. Yeah, so this means that in this case, instead of having a functor between two different categories, and then 2 discrete vibrations into each of those categories. We're now looking at the case where there's just one category, and you still think of there being a functor, but it's just the identity functor, and you're really just focusing on that you have 2 different discrete vibrations into the category S. And you can map between them. And I'm gonna assume I don't know if this is gonna become the focus, but I guess I'm kind of considering that what we're actually going to be doing is we're going to take a single category, and then we're going to look at all the different discrete vibrations into that category and the maps between them, and then we're going to study them in some way. It's going to reveal something interesting. We denote, we denote by D fib S A B the class of maps of discrete vibrations over S. So now, I don't know, I assume you could do some interesting studying of discrete vibrations where they don't share the target category, but for the time being, it just seems like they only set up that definition so that they could lead us to study discrete vibrations into the same category. I don't know if this is a good metaphor, but it's almost like a wheel or something. Like S is the hub, and you're just looking at all of the different arrows into S, which are like the spokes of the wheel. And another thing to consider is that in the category of sets, functors are the morphisms. So now I'm wondering, what are the categorical properties of discrete vibrations as morphisms in the category in the category of categories. I don't know if I just said the category of sets. I got confused. In the category of categories, and I think that's kind of how you do internal category theory or categorification, where it's you recognize that it has some kind of universal property, and then once you find that universal property, you can just go back to other categories, like the category of sets, and realize a discrete vibration, or the class of discrete vibrations. The class of maps between discrete vibrations. It kind of reminds me of, I think it's called it's either an arrow category, or it's a home functor or something. It's you choose one object, and you just look at, or the slice category or something, you look at all the morphisms into or out of that object. So I'd love to explore that later. And I will draw a little picture. Okay, so we have some object. We have arrows coming into it. And then we're curious about maps between these arrows. And we have the same thing, except for this is a category. And these are specifically discrete vibrations. Whoopsie. And then my question that I'd like to pursue is, whoopsie, 1 second. Is we have this, I don't know what to call it, conventional or straightforward definition of discrete vibrations over S. I think that's correct to say. Discrete vibrations. Discrete vibrations over that's not correct. It's the discrete vibrations. I guess you would say it's the... No, wait, what do you say? Yeah, never mind. Yeah, it's the discrete vibrations over S. If this is S. Yeah. I'll think about this later, but I want to know, like, what happens when we take the structure out of the category of categories and we look at it in, like, the category of sets or something. If this is just a set, and these are just functions, you know, what kind of functions would they be? I'll explore that later. For a small category, we will refer to the category of small discrete vibrations. So that's cool, because I was hoping that we could study this categorically, and apparently we can, as long as we restrict it to small categories. And their maps is dfib_s. So basically, in conclusion, if you ever see dfib_s, you are looking at a category of maps between discrete vibrations into the same object. And just remember that discrete vibrations are functors. And so you're basically looking at, I think, a category of functors. And now I'm thinking, but when you map between functors, isn't that usually like a natural transformation? And I also think there's something that I'm still learning about, like the Uemura lemma and stuff. It's something like you map each object, or the Uemura functor, something Uemura construction, you map each object into its like home category or something. Like, yeah, okay, I need to focus on the details, but I feel like there's some connection here that I need to learn. And anyway, that was just the definition. My goal is to prove proposition 3.2 and then say I did learn something today. So here we go. For a functor, the following are equivalent. P is a discrete vibration, or the diagram, this is a pullback. And I don't understand this. I don't know. This is like, I guess a codomain. Wait a second. So A is a category, P is a functor. I guess some kind of codomain map. I would think that maps an arrow to its. Wait a minute. It maps a arrow to its codomain or target object, I would think. But let's see. Oh yeah, maybe this is like the arrow category or something. Let me just say that more. Let's just say that we have like, yeah, something like all the arrows in S. And it's just mapping them all to their codomain. But if this was truly categorical, I think you would call it the target. So I'm wondering if codomain is like used because it's associated with the codomain of a function in the category of sets, or if there's something else that I don't understand. And it's saying that this is a pullback, and I was trying to get it, like, I can't remember. I need to study the difference between pullbacks and equalizers. Wait, actually, no. I think I understand that. I think this is an equalizer. And this is a pullback. So they're like very similar, except I don't know if this is true, but it would be cool if an equalizer is a special case of a pullback where these two objects are the same object. That would be cool. And these two errors would have to be the same error. So it's actually two different things. So one thing is like, when we talk about the equalizer of two arrows, we're talking about an arrow. But when we talk about the pullback, we're talking about more about an object, I think. Because in a way they both start out as spans or cospans. So like here we have a cospan, and if it just turns out that it's actually cospan, where both arrows are from the same object, then maybe we could just shift this over, like this kind of comes over here, and now we're just looking at this. And then this is going to be the pullback. And on a side note, I think I read recently that in the category sets, pullbacks are unions. If that's true, that's really interesting. Or something like that. Now in this case, let's see. I'm going to do my little set thing, diagram thing, drawing thing. The idea here is like, if this was set theory, let's say. So we have some elements, and we have more elements. I'm going to change it up this time. This set is going to have larger cardinality than this set. This one's going to have smaller. Okay, here we have a map that we know cannot be injective because this set is larger, and if we're talking about finite sets, I haven't thought a lot about infinite sets yet. But it does not have to be surjective, so we shall do this. Here we have a map that we know cannot be surjective. This cannot be injective, this cannot be surjective. Let's go like that. And we want to know if there's a set where, if we think of a function or a mapping as a way of like selecting elements here and selecting elements here, so that each element here ends up at the same place. And I think that's a cool way to think about, like, it's almost like a really easy way to construct a pullback, I think, instead of wondering like, oh, but is there a pullback? It's like, well, all you have to do is, one second, let's give it like 4 elements. All you have to do is make choices so that you end up in the same place. So like, we know that these 2 elements are going to here. So that means that, actually this might not be true, but I'm thinking here. I want an object, and I want 2 maps. Yeah. So that we end up in the same place. So I think the simplest thing you could do is just map everything to this element. And map everything to this element. And I'm going to call this X, Y, Z, P. Oh, crap. Maybe this is very wrong. Oh, well. Okay. F. G. A. And B. And like, obviously, F does not equal G. Darn. Yeah, I'm going to move ahead, but I'm just going to say clearly F, when applied to like all elements on the set Y, I don't know if that's valid notation. I guess you would say the image of F, right, on Y or something, is not equal. Wait a minute. Okay, yeah. I might be just going off in like too many directions of confusion. I'm actually going to step back here because I do think that I've kind of taken a first like account of the situation, and my mind will like clean it up over time. Anyway, there's some kind of pullback here. A discrete vibration. If you have a discrete vibration and you have some kind of codomain functor from, I think, like the arrow category or something, then it turns out that if that's like an arrow category of the indexing category, you can either map it via this codomain functor, or you can map this arrow category to that arrow category. And I need to study the specifics, but I think the theme corresponds to what I was trying to say above, is like in a discrete vibration, there's like a very like controlled relationship between the morphisms that are being mapped. And so here they're saying like, you know, maybe this is that categorical universal property that I was wanting to know earlier, that maybe we could like move to the category of sets or something, which is that, yeah, I need to remember the definition for the arrow category, but basically I think one way you could think about this is like the information in the vibration is like accurately conveyed in the arrow categories or something. And I mean, it opens many more questions to me, like, you know, you can take the arrows in this direction, but what if you could take the arrows in the opposite direction or something like that? For any object A, the functor A over A, and I believe that's the slice category, mapped to S over P over A, induced by P, is an isomorphism. So, there's an this is another thing that I kind of like thinking about or asking about, is that for a discrete vibration, the discrete vibration induces like an isomorphism between all possible slice categories, I think is what it's saying. And for me, maybe that's almost like a nicer definition, because maybe that's kind of like, this definition is just like setting you up for this definition, and this definition is like a very it's like a clear expression of, you know, what's really going on, what is a discrete vibration all about, what property does it have. Is that, let me see if this is correct. You have your objects, And then you select one. And the slice category, I think, is all of a sudden you're looking at arrows. I'm not sure if it's into and out to and out of, but you're looking at like arrows as the objects. And now this doesn't really correspond to this, but whatever. So we have all these different arrows, and it's understood that they are all arrows, let's say, into object A or something. And there's a slice category under, and there's a slice category over, and I can't remember which is which. Oh well. So this it's understood these are all arrows into A, and then morphisms between these objects, which are also morphisms but not in this category, are morphisms. So you almost like, maybe that's why it's called the slice category. It's like you split apart all of the morphisms actually, which is very cool. And some of the morphisms become objects, and some of the morphisms become morphisms. So let's see. Let's just imagine that we can do this and this. And okay, so let's say this is category A, and this is category S, and we have another kind of slice, but we're going to focus on how this is, there's a functor, and it's a discrete vibration. And that tells us that there's an isomorphism here. And yeah, again, I'm not going to worry too much about the details. I want to just get through this proof if I can. I might actually type this. Let's see. Okay, so the implications 2 to 3 and 3 to 1 are immediate, which shows you that I need to learn a lot more because to me it's not obvious. To see 1 to 2. Suppose that P is a discrete vibration. By definition, the functor, this is the pullback, and we have a functor from A arrow to the pullback, which I assume we're eventually going to find out is also a arrow, but we haven't shown that yet. So by definition, A has its own error category if this is the error category. And by definition, if A and S arrow have a pullback, it's bijective on objects. I need to study this. To see that this functor is also fully faithful, let F be objects. Be an arrow. So there's this unique arrow. Okay. Okay, so if it's going to be bijective on objects, the thing is that I believe the objects of the arrow category are arrows. And I'm pretty sure the arrow category is the one with commutative squares. So like you map one arrow to another if you can find a map from the domain, the source and the source object, and the target and the target object. And the pullback of A, which is just some category, and S, the arrow category of S. Let's see. Arrow category of S. So there's some reason that, yeah, that's interesting. Let me think about this for a second. So you have A, and you've got its arrow category. You've got S, and you've got S's arrow category. And here they say, suppose that P is a discrete vibration. And then they say by definition, and I'm not sure if they're saying that like by the definition of a discrete vibration. Well, wait a minute. Yeah, I'm not sure if they're saying by definition of discrete vibration or by definition of an arrow category and a pullback. 1 second. The functor is bijective on objects. Okay. So we have a functor from arrow category of A to their pullback, which is So okay, yeah. So there's some like illusory pullback here, which is A product S arrow. And if that pullback exists, we think that this diagram commutes. And now I feel like it's clear that there's a lot of information here to be explored to prove stuff like this, because 1 second. So this, okay, so this is P, and we've just been told to assume that P is a discrete vibration. And this is a functor from the arrow category to the category. I don't know if I completely screwed this up, but anyway. And now they're saying that this, what was that? That this functor has to be bijective on objects. And yeah, I need to think way more about why that is. What does that sound? I don't know. To see that this functor is also fully faithful, which I believe means it has something to do with like surjectivity and injectivity on home sets or something like that. And yeah, I'll look it up later. Let F1 be a map from object A1 to A prime 1. Okay, so let's assume that here's our category, And we have a map. And we have another map. Oh, actually they're in the arrow category, which is over here. Let G be an arrow in A. And here we see this correspondence. So we have A1 prime. So in the arrow category, these are the objects. In the original category, one second. A1 prime, A2 prime, and I'll just write in parentheses or something that this arrow is associated with A1 prime. So now we know that there should be an arrow. I think there should be an arrow G here, but it will be an amorphism in the arrow category, and we'll need some other arrow here to make that happen. Let U P A1, so U P A1 be an arrow in S. That makes sense. Let's add these in here. So these are the objects that these arrows are associated with. And they exist somewhere in here. And also, these arrows also exist somewhere in here. And then it's saying that we take our discrete vibration over to S, and then we have an arrow, which we call U. And then, okay, one second. Now we have the functor. Yeah, let's see. Yes, so this is F1. Damn it. Here we have F1 and F2. And our discrete vibration. Mapsies. Wait, so P of A is here. Shoot. Think about this. So if we're mapping them, let's see, this goes to A1. So if the functor maps this morphism, then it means that we have this, and then we have P of A1 prime, and we have F2, and then we have P of A2 prime, and G has to be mapped to something, so I guess that's probably the condition that's going to come. Second. So P of F2, which is right here, composed with U equals P of G composed with F1. So this is P of G. And I hope I am correct in just calling this a coherence condition, which I need to study and think about more. But we have like a little commutative diagram here, I believe. And this is saying and suppose. So it's an assumption rather than like a proof that it, or like a claim that it follows. So I'm going to zoom out and refresh what I'm talking about here. We started out with a functor between two arbitrary categories. We assume that it's a discrete vibration. We also form arrow categories from each of these categories. And then I'm pretty sure that there has to be a functor going in this direction to form an arrow category. Like I assume that there's like a universal construction or something. There's one like way or canonical way to make the arrow category. Maybe there's only one way, just in general, unique or whatever. Yeah, so that's kind of a question. Then I can't even remember where this arrow came from. Oh, that error came from the fact that this is a pullback. But we don't know that it exists, right? Yeah. Actually, maybe. Oh, no. Because. No, wait. Let's see. It might have to do with this. 2 leading to 3. 3 leading to 1. Functor, slice category. Yeah, I don't know. So, I'm going to say, if there was a pullback, which we don't know, yeah, there's a lot to think about because I'm trying to think about is there a canonical mapping from the error category back into the base category, or are there like different options, or is that kind of like a forgetful functor? Like for algebraic structures, you just forget the structure. I mean, maybe there is because maybe you can use like equivalence classes or something because I'm gonna assume there's only one there is only one arrow category possible. It's uniquely determined. So I think that should mean like, well, that's another question, but I think I'm very confident you can always reconstruct the original category from the error category. It's like it contains the same information. So let's just assume like Um, or I don't know. Let's hope or assume for now that this is possible. So if my assumptions are correct, what I'm saying is, for any category, you can always construct its error category. And I hope you can also always get back. This needs to be examined further. Now we assume we have this functor, which is a discrete vibration. And we're going to imagine that there's a pullback. And I would also like to imagine that this immediately induces like something like this, but maybe that's part of the proof. I don't know. Okay, so we have this pullback. And then they're saying that there's a functor from this to this, and that it is bijective on objects. And I truly cannot justify why that is, but I know that I can if I think more about it. Seems like a very good exercise to think about that. And then they want to show that it's also fully faithful, which is like, so they kind of got some conditions that they wanted on objects. Now they want to get some nice conditions that they want on arrows or home sets. Okay, I'm just gonna say, like, I learned a lot. It's too bad that I couldn't get to the end of this proof. I tried, and I'm gonna think a lot more and come back to this. Actually, I take that back. I am gonna finish this because that's why I'm recording this, is to motivate myself. Let's keep going. So, let U, P of A, be an arrow in S. So we have an arrow here. U. And it's coming from two objects in here. I'm actually going to put these drawings next to this diagram. So we have A and S. We have U from P of A1. P and I'm also thinking U is a map of something over here. But I don't think we've been given a name for it yet. We have this. suppose that P of F2 composed with U is P of G. Get that down there. P of F2. At this point, I'm thinking like if my drawing was not so sloppy, it would help me a lot, because now I'm like just confused by the sloppiness of my drawing. But I'll improve on that in the future. P is getting mapped down here, and these are getting mapped down here. So A1 prime. And we got our maps. Let's see. And then we must assume that now I'll kind of like extract this diagram to make it easier to see. It's like a little magnifying glass or something. I'm sweating. It's hot in here. Okay. And then we have G as well. So the coherence condition is this, that this diagram commutes, I think. P of F2 composed with U is equivalent to P of G composed with P of F1. And I think that means that what we have is like a mapping from P of A1 to P of A2, and it's like it tells us something like, you know, I don't know. I'm gonna assume like there's something very like important about this mapping morphism, because like, yeah. we have to show that there exists a unique arrow in A from A1 to A2. We want to find out if this error exists. Call it U hat. Which gets mapped over to U. And then I'm literally sweating and I need to finish this soon. And such that f of 2 composed with U hat is equal to G composed with F1. So we want to put an arrow in here, and then that I think you can say that arrow like would induce like a unique arrow here or something. Such a U hat must be U bar, which is the notation for a discrete vibration, I think. When we have that, and then we put A2, I believe that means that it's the, oh man, let me think about this now. Go back up. Oh, such a unique arrow. Okay, so this is not the vibration, is it? No. There exists a unique arrow. Oh yeah, so that's like the unique arrow that makes a discrete vibration what it is. And they're saying, because it's a discrete vibration, we know that this arrow exists. We know that it's something like every arrow in the target category is mapped to by like a unique arrow in the source category or something. It's like something that simple, I think. Oh shit, you know what? I think I learned that a long time ago and I forgot. But that's like a much simpler definition, I think. Yeah, I think that's it. There we go. Okay. I do remember learning this a long time ago, or some months ago. A discrete vibration is injective on morphisms, but a lot of the time we talk about like conditions on functors regarding morphisms regarding like home sets. But a discrete vibration, it doesn't care about home sets. It just cares about the collection of all arrows, and it's 1-to-1. I think, and yeah, I think that's a really simple definition. I'd like to think more about that. Such a U must be one second. So this star, now I understand the star is kind of like an operation. Let's see. think. Yeah, so yeah, this part I don't fully understand. When P of A is a discrete function, A is a discrete function O as refer the function P for discrete function A or as just unique arrow. Okay. Okay, so for any arrow in the source in the target category, which we refer to as U, which is essentially pointing at something, let's say indexed by A in the source, then there's the unique arrow. So this I can write down. Okay, so we think that in the target category there is an arrow, and we're going to say that it, we're going to call it U, and we're going to say that it came from A in the source. Or sorry, it goes into something that came from A in the source. And we are going to refer to the arrow that it came from, which we know is unique, as U bar A. And I don't know why that notation is chosen, but yeah, trying to figure this out. Huh. Yeah, I would say I don't fully understand this because U is a morphism in the target, and A is an object in the source, and I don't know how they can like be multiplied. I don't know. Yeah. I'm gonna have to think about that or ask someone for help. So I'm gonna say, yeah, I'm gonna say this is kind of like a hang up for me right here. I understand when you see U hat, you can understand it as the unique morphism that U came from the discrete vibration or functor, but I don't understand why there's this little like star or multiplication symbol, unless this is kind of like an arbitrary notation, like it's just their way of saying, oh, just think of like some U, which is like, let's say tipped or pointed by A, or rather by P of A, and which, you know, in the, if it's just like a so-called abusive notation, like it's just you shouldn't read it like as an actual function. I don't know, but whatever. So it has to be, there we go. This, they are saying that we want to know if this functor is faithful, or rather fully faithful. We want to know if this arrow exists, and it apparently does, because that's the condition of a discrete vibration. Yeah, and I'm gonna say I did try to study this I got to the end of the proof basically, and I know that there's a lot of stuff that details I need to fill in, but I would say I did okay, got to the end. I guess I will read the last line. It indeed satisfies F2 of U hat A2, which is also this thing here. Equals GF1, since both F2 of U hat and GF1 have the same codomain and are sent by P to the same diagram over here. Yeah, and that probably has something to do with like the fact that it's a pullback or something, or yeah. So I'm finally ending my video here. If you watched this whole 2-hour thing, thank you for having an interest in my studies in mathematics. And yeah, have a wonderful day.